Coming to this open night, one of a long series of open nights, of course. It's my great pleasure and special honor to introduce Jonathan McDowell, my good friend and colleague for these many years here at the Center for Astrophysics. Jonathan and I, as you will tell, emigrated to this great country from the old lands in the UK. He came by a much more prestigious route than I did, though. Well, Cambridge is not a bad university, you know.
It's okay.
Yeah, okay. So we give it away. We give away your secrets. Okay. Jonathan is an excellent astrophysicist. He is far better than average as a programmer among scientists. In fact, I'd say he's probably, what do you call it, a good hacker. He is a manager, and in fact, I actually resigned my position as a manager in his favor, like Isaac Newton got his job in Cambridge, of course, from a lesser person. And what else? Oh, yes, and I also exploit him ruthlessly as my mathematical sidekick because he's much better at algebra than I am, so that's really good to have around. But that's just his day job. And his real claim to fame outside these walls is not so much for his astrophysics, but for his immense, deep knowledge of everything that's been launched into space since the very beginning, since Sputnik. Anything that crossed the von Karman line, he's got it in his database. He has the world's, I would say, the world's best database. He's nodding modestly. The world's best database of anything that's ever been launched into space. Right? I think he doesn't actually include the contents of a locker, but it has to be free-floating, right? So, yeah.
Or bolted to the outside of the ISS.
Ah, okay. It can be bolted onto the space station. That's okay. It is a measure of how good his database is, that he has been a paid consultant to ESA to provide better data than they could do, the European Space Agency. NASA also takes great notice of what he's got in his database, and even the Department of Defense keeps good track of what he publishes in his monthly monthly Jonathan Space Report, which simply lists everything that's ever been launched in since the previous report. And the people who in the know really keep up on this, every little detail. In fact, he collects all the technical numbers that most people are allergic to, the precise date, time of launch, and the injection, and the orbit. And his idea for many years, his idea of a really great vacation was to go to the basement of the Goddard Space Flight Center, open a bunch of filing cabinets, and copy, Xerox, it used to be called, every piece of paper he could get about the technical details of everything they'd launched. And many people at NASA had forgotten they had this information, so that's why he's able to have a better database than NASA. Quite impressive. But one of the pleasures of being at CFA with Jonathan is that many times a week he'll come in and we'll have a little chat about everything that's been launched into space in the last week or so, and I don't go for the same technical level of detail, I must admit, but there's so much going on with Elon Musk and Jeff Bezos and all sorts of other interesting new space startups that we have a lot to talk about all the time. And one day I asked him, I got hold of this little book. I think my daughter gave it to me as a Christmas present, called Exploring Space. It was published in 1964. And I said, Jonathan, are these actual pictures of real things? And so for those of you who are not in the room, I'll just show you this a little larger. Where do we start the slideshow? Here we go.
Slideshow.
There we go. That's the little cover of this little British book, published in 1964. And so that's on the inside page, and you see he started annotating it for me. He said, oh, well, yes, obviously that's a Vanguard rocket. It had 3 successful launches, and a little note here about how there was an earlier version that was simpler. And then he glances at this. Oh, well, that's the Atlas D, and a Mercury capsule. 109D was your guess for that?
Yeah,
not guess, excuse me.
Written on the side, isn't it? But, yeah.
Oh. It's a painting. How can it?
All right, okay.
He's so observant. Right. And then I show him this strange thing. He said, well, that's Luna 3. Everybody knows that was the first instrument to take a photo of the far side of the moon. And then the last one was this. I said, well, what crazy thing is this? Well, he said, that's trickier because it could be EPE A, B, C, or D. Better known, of course, as Explorer 12, 14, 15, or 26. And EPE stands for Energetic Particle Explorer. Do you think you can resolve this terrible dilemma at this point?
At the level of detail they've drawn it.
I see. It's not his fault. So you can see that there is no one around who is better qualified to talk to you about what's been launched into space, and in this case of today's lecture, what has not come down. What goes up does not come down necessarily in space, and so Jonathan is going to talk to us about space junk. How do I stop this? Here we go. Click to exit. Good.
Don't break it.
There you go, Jonathan.
All right.
He knows my technical skill as well. How do you know? There you go. Thank you.
Thank you, Martin. This is going to be your test for figuring out what all of these are at the end. So it's now 60 years since the launch of the first artificial satellite of the Earth, Poszczeszczy Sputnik 1, the simplest satellite #1 from Baikonur in Kazakhstan. This is a picture of the launch, and this is the 83-kilogram satellite that it put into orbit. But you may not know, probably most of you have heard of Sputnik, yes, you may not know that actually Sputnik is the second object in the catalog of satellites that we keep. The first object, catalog #1, was this rocket stage that put it into orbit. Because when you launch a satellite with a rocket, the rocket stage has to go into orbit to get the satellite into orbit. And so the very first orbital space launch had a big piece of space junk that re-entered after a few months, but still. And so what you do when you're going into space is you launch a rocket up through the atmosphere, get out of the atmosphere so there's no friction, and then you go sideways for a few minutes, building up speed to the magical orbital speed of about 17,000 miles an hour. And that's how you can stay in orbit. I'll say more about that later on. And so what you do is then your rocket switches off, you're at the orbital speed, you just fall around the Earth, and now you separate the satellite. But the rocket's still in orbit. And so that's one source of orbital debris, which is the technical term for what most people call space junk. So why is that a problem? So I want to introduce you to my friend Iridium 33. It was a half-ton communication satellite launched in 1997, and it was zooming around the Earth quite happily for 12 years, working, relaying cell phone communications. And one Tuesday it met this guy, Cosmos 2251, which had been a Soviet Ministry of Defense communications satellite, but for many years it had been inert, it had been switched off, and when you switch a satellite off, it doesn't just come down, it stays in orbit right where it was. And so it was orbiting the Earth as a piece of space junk. And 480 miles over the Arctic, Iridium was orbiting the Earth like this, pole to pole, and Cosmos was orbiting like this, pole to pole. And so they come in, the relative velocity at which they said hello to each other was 26,000 miles an hour. Now, yes, ouch is the correct analysis here. And let's say, but you know, ouch would be, I think, imagine a 1-ton truck hitting you at 100 miles an hour. That would be ouch. But as many of you may remember from high school, a half mv squared kinetic energy, if you go 10 times faster, there is 100 times more kinetic energy. This is why you should obey the speed limit, Boston drivers. And so this, compared to the 1-ton truck at 100 miles an hour, this had 54,000 times as much energy. So that's a big ouch. And so a few hours later, what you see is this string of pieces of debris along the individual orbits. What happens in a hypersonic collision like this, it turns out, and the Department of Defense did an experiment to determine this, you smash into each other at 26,000 miles an hour, a hypersonic shockwave goes through both vehicles, reduces them to confetti, and the clouds of confetti pass through one another without really interacting much. And so they end up pretty much on the same orbits that the original satellites were on. I remember to turn off my phone. And so pretty soon, and then various complicated effects mean that these sort of trails of pieces of debris spread out into a shell around the Earth, so that they're there for any other satellite to hit them. Currently, the radars on Earth can track things that are maybe a few inches across. We have about 2,200 pieces from this collision in the catalog. Now, some of them are re-entered. About 700 have re-entered, but that's still well over 1,000 pieces from this 2009 collision that are still in orbit. So that's why space debris is a problem. Even small pieces are not good. The smallest things we catalog are typically a couple of pounds, typically a few inches across, and that's like, if that hits you, that's like a 1-ton truck at only 1,000 miles an hour. So it's still like being hit by a missile. And here's a French Defense Ministry satellite that got its antenna taken out by a piece of debris back in 1996. So these collisions happen, not too often. The really big ones maybe are like the one every 10 years point right now. But here's the problem. We're launching more and more satellites. And this is another of these squared problems, that if you have 10 times as many satellites, you have 100 times as many collisions. And so if it's one every 10 years now, if you have 10 times as many satellites, it's going to be one a month. So there's another problem with space debris that you might worry about, which is that it might crash to Earth and cause lots of damage. There's been some media press about that recently. But the thing is, when you enter the atmosphere, so you're orbiting the Earth, and if the Earth didn't have an atmosphere, you'd just orbit forever and ever, falling around the Earth, just like the Moon does. It's far enough away it doesn't feel the atmosphere. But if you're even 500 miles up, 300 miles up, there's just a little bit of air. Not enough to breathe, millions of times less than what's in this room. But if you're going at 17,000 miles an hour, that still makes quite a headwind. And it slows you down. Imagine sticking your head out the car window on the freeway, right? Now imagine doing that if the wind is 17,000 miles an hour. And so it slows you down, and you spiral in closer and closer to the Earth. And the closer you get, the denser the atmosphere is. And at a certain point, it gets so dense that you're really heating up because of the atmosphere. The energy of the molecules hitting you is making you hot. You melt, you break apart. And most of the space junk that comes down just melts up completely. But the big chunky ones may be so big that they re-enter so quickly that it hasn't had time to melt all the way through. They have dense materials. A lot of satellites are made mostly of aluminium. Or aluminum to people here, and so they'll that has low melting point. But there are pieces like rocket engines and so on that are made of sterner stuff that can get all the way to the ground. The biggest ever that came down was the 75-ton Skylab space station in 1979 that scattered pieces of itself all over the Australian desert. And nowadays the practice is, if you have a big thing like that, you have a rocket engine on it, and when you're done with it, you deliberately bring it down under control in this area of the South Pacific called the spacecraft graveyard, which is, there's a piece like southeast of New Zealand which isn't on the way to anywhere, unless you're a penguin, and so there's no like shipping lanes and air lanes, and so you can just burn it up over there without worrying that you're going to hurt anybody. So that's what the big ones mostly do. But there have been a few incidents. The most notorious of which was the Soviet Navy satellite Cosmos 954 in 1978, which had a big radar to track American Navy shipping. And that big radar needed a lot of electricity, so they put a nuclear reactor on it. They had a whole series of these things. And the rocket engine stopped working, and it re-entered and spread radioactive debris all over Great Slave Lake in Canada. And you see here pieces of spacecraft metal melting holes in the ice because of their radioactivity. So this was really not good. And occasionally you get fuel tanks of rocket stages that they're big empty tanks and they get banged up a bit in re-entry, but they kind of float down. And so here's one in Texas from a Delta rocket, very similar design of one in South Africa. Here's a fuel tank from a Russian satellite in Brazil. And so the satellite, breaks up into little pieces, but a few get down. But no one's actually been hurt by re-entering space debris, except arguably for Lottie Williams here of Tulsa, holding the piece of space debris that floated down and hit her on the shoulder. She wasn't hurt because terminal velocity was low and this was kind of just really floating down. But she's the only person we know of who's actually been hit by space junk. So the biggest reentries to come down, I said Skylab, almost 80 tons, came down in 1979. The rocket stage that put Skylab in orbit also came down at 775. That was 49 tons. And the Salyut 7 space station with an attached module, 39 tons, came down in 91. Those were the big ones that came down, not in the spacecraft graveyard, not under control. Those were bad. We don't want those. There's been a lot of press lately about a Chinese space lab called Tiangong-1, which is re-entering probably around January. It's only about 8 tons. It'll mostly burn up. Maybe a little will reach the ground, but we get something like that once every few years. So I think there's a lot of overexcitement about it. So that's the two things that can go wrong. Space junk can hit your satellite, or it can fall on your head. So how big a problem is this? How much junk is there? So this isn't the junk. This is the working, useful satellites versus time from 1960 to the present day. And if you think about the height of the space age, you think of the 1960s maybe, but there were only, a few dozen usually active satellites working at a time back then. Now there's almost 2,000. See how steep this curve is? We're using space a lot more than we used to, and the trend is straight up. What are we doing up there? These are the main kinds of artificial satellite that we have going around the Earth. Communications satellites, maybe 6 tons, usually sitting in geostationary orbit 22,000 miles over the equator. Earth imaging satellites, maybe for Google Earth, maybe for a 3-letter agency that's spying on somebody. Those are typically a few hundred miles up going over the poles in what's called low Earth orbit. There's also a category of signals intelligence, which is exclusively for the military, listening into radars, enemy radars, and maybe your phone calls. There's a lot of little tiny technology satellites. I'll talk about those a little later. And of course, half of you wouldn't have been able to find this place today without the GPS satellites. And then there are some science satellites like Chandra here that Martin and I both work on and is continuing to return exciting science. And also spaceships with astronauts on board, they're satellites too. And so I did sort of the breakdown of what they're used for, and by number of satellites. The biggest things are either communications or imaging. and the technology satellites are pretty common too. The trick is that the technology satellites are mostly really tiny, whereas these ones are big. So most of the action is in imaging and communications. And you'll see that science is really a small part of the pie. And the people, who's doing all this? I've shown here the people who own satellites and the people who build satellites. And the answer is pretty much the same, that the big players in space are the US, Russia, Europe, and China, with India and Japan kind of the next tier down. And the division is between civilian, defense, and commercial about equally. And non-profit is coming up. This is university satellites mostly. And that number of satellites, if you look at maybe a better proxy for how much this all costs, is the weight, the mass of the satellite. And so I divided it up that way. And by mass, the human spaceflight, this color on the left, is the most, because this is all the stuff launched since 2010, and that included some space shuttles and some space station modules. The space shuttles are 100 tons each, whereas these, the little technology satellites here are often a couple of pounds, and so they don't show up at all when you do it by weight. But if you ignore the human spaceflight, which is a lot of the money, it's sort of equally divided in effort between civilian, military, and commercial now. And so most satellites are either in low orbit a few hundred miles above the Earth or in this geostationary ring at 23,000 miles. So the geostationary ring, right, is that if the higher you orbit, the longer it takes you to go round. If you're orbiting just above the Earth, you go round the Earth in 90 minutes. If you're at the distance of the Moon, it takes you a month. Not coincidentally. And in between, it takes intermediate amounts. So somewhere in between, there's a height at which it takes you exactly a day. And if you're in an orbit that takes exactly a day to go around the Earth, and the Earth is also spinning once a day, you keep pace with somewhere on the ground that beneath you. And so it seems to someone on the ground that the satellite isn't moving, and that's why if you have a direct TV dish, you don't have to keep moving it. So the geostationary orbit is very popular for that reason, which is why there's so many satellites there. So, and just to reemphasize, some of these satellites are really tiny. So starting in 2003, they introduced the CubeSat, which is 4 inches, 2 pounds. There's a triple version that's very popular, that's like a foot-long hot dog, basically. You know, in 2000, they launched a few of those a year. This is how many of these CubeSat launches per year, until about 2013, and suddenly they started launching 100 a year. They finally got the electronics and everything miniaturized enough that you could do something useful with one of these tiny satellites instead of just, have students build it and have a webcam and go, oh, we built a satellite. And so now companies are building these satellites, and they're going up at the rate of 100 a year, and that's really, really changing the sort of demographics of the satellite population to have all of these small satellites orbiting the Earth. At the other extreme, this is the biggest artificial Earth satellite. This is the International Space Station, 420 tons. So if you think of one of these 4-pound, 1-kilogram CubeSats, this is 420,000 times. It's 500,000 of the CubeSats to make one of these. So a lot of the weight is in this one thing. But now I showed you that curve of how going up really quickly the number of active satellites. I've replotted it here in red. See, 2,000 number of active satellites going up. But these other colors are all the different flavors of space junk that go along with that. And so you can see that most of what's up there is space junk. So we have in black dead satellites, things that used to work but now are just falling around the Earth inert. Rocket stages, because like I told you, you launch the satellite with a rocket stage. This is sort of what I think of as general littering. If you have a lens cap that you eject, if you have two satellites and there's a little widget that separates the two that you throw off, anything else that you throw away that isn't in the other categories. And then this big green tranche is the other kind of debris, which is generally explosions of one kind or another, and we'll get into that in a minute. You see there's a lot of that. This is the shrapnel. And then in particular, you'll see that in 2007, there's a huge jump in the amount. This black stuff suddenly appears. That's from a single incident. That's from the Chinese military's anti-satellite test in 2007. And so they exploded this satellite. They did it in just the worst part of space. They generated huge amounts of space debris, and we'll see that later. And then the cyan, the light blue at the top, is another jump in 2009, and that's that collision that I showed you at the beginning, the Iridium satellite that hit the Russian satellite. And so just two incidents are responsible for a huge amount of the space junk that's currently up there. This is the same thing, but by weight, to say that there's currently almost 9,000 tons of stuff in orbit, and almost 80% of that is junk. And so the worry is that as the amount of junk is increasing rapidly, we get this n-squared problem, 10 times as many satellites, 100 times as many collisions. And we could enter a chain reaction that's known as the Kessler Syndrome, where you take all the satellites in space and they all hit each other rapidly, and you end up, instead of having a space program, you end up with Saturn's rings made of aluminum. And you're unable to use outer space for the next 100 years or something. So we really would like to avoid that. And so at the end of the talk, I'm going to talk about some ways in which we're trying to improve things so that we might still be able to use space and not completely mess it up. But first, we're going to do a little digression. Namely, we're going to just talk a little bit about what it means to be in orbit and what kinds of orbits there are. So I find out that not everybody, some of you already know this, so bear with me. There's a very big difference between being in space and being in orbit. So suppose I just go up into space 200 miles, switch my rocket engine off. What happens? I'm going to fall right back down. And so that's why when I launch the satellite, instead I also make sure I'm going 17,000 miles an hour sideways. And then in 1 second, I'll just, by high school math, you can do like in 1 second, you fall about 30 feet under gravity. But if you're going sideways that fast, at the same time, you've gone sideways 5 miles. And in that 5 miles, because the Earth is round, everyone's with me on that, right? No flat earthers. The Earth will curve away from you by 30 feet. And so you've fallen 30 feet, but you haven't gotten any closer to the Earth. And so you can repeat this trick to fall all the way around the Earth without using any fuel. So if you extend that, after almost half an hour, you've fallen 4,000 miles, and you would be in the middle of the Earth, but you've gone sideways 4,000 miles too, so you missed the Earth entirely. And this is where the really neat part of the trick comes in. So you had this sideways speed that you used to miss the Earth, but you're still picking up speed from gravity as you fall. But now you're over here, the downward speed that you got from gravity, which was a falling speed, is now a sideways speed, because the Earth isn't over here anymore, it's over here. And so you've turned the gravity, the falling speed, into a new sideways speed. And so gravity's now pulling you this way, but your old gravity speed is making you, helping you miss. And so then I would just turn your heads 90 degrees and repeat what I just said. And you can just fall all the way around without using up any energy. So that's what orbit is. It's as Douglas Adams says, the secret to flying is to throw yourself at the ground and miss. and that's as good a description as I can give of what's being in orbit. So for those of you who are complaining about no math in this talk, just remind us, I'm just sort of throwing up, it just comes very simply from Newton's law of gravity, from the Kepler speed that you have to be at, is 17,000 miles an hour, and then you get Kepler's third law, which tells you the higher you are, the longer it is to take to go around the Earth. But you don't care about that. So what paths can you take? And one of the other really important parameters that I want to talk about is what we call the inclination. And the inclination is just, are you going round the equator? That's a 0 degree inclination. Are you going over the North Pole, South Pole, North Pole, South Pole? That's a 90 degree inclination. And something in between, like the ISS, it's at 51 degrees. What that means is it goes as far north as 51 degrees north, comes round, goes as far south as 51 degrees south, and up again. And the trick here is that what you're not allowed to do is the yellow curve. You're not allowed to go in a circle around a line of latitude, right? Gravity says that your orbit, the circle of your orbit, has to have the center of the Earth at the middle of it. You can tilt it, but you can't just move it up and down. The other trick is that the Earth rotates, and once a day, and it does so if you're sitting on the equator about 1,000 miles an hour. So if you launch from the equator, you get a free boost of 1,000 miles an hour. And if you're at the poles, it doesn't work, right? Because you're not going anywhere if you're at the North Pole. But even at the latitude of Florida, Cape Canaveral, to take a random example, you're still getting 900 miles an hour free speed. So you're going to launch east to take advantage of that free speed, and not west, where you'd have to add an extra 1,000 miles an hour to get the same satellite into orbit. And so we launch to the east and get this to this critical speed to get into orbit. So what I'm showing here is where all the satellites are, and along here I have, this is sort of a log scale from just a few hundred, I'm sorry, it's in kilometers, 100 kilometers above the Earth, so a few hundred miles above the Earth is where most of the stuff is. And then there's kind of a gap, and then there's this spike here, which is the magic geostationary height where it takes 24 hours to get round. And so in green are the satellites that are working, in red are the satellites that have died, and in black is the rest of the junk. And so roughly speaking, the satellites and the junk are in the same place, as you might expect, and they're mostly either in LEO, low Earth orbit of a few hundred miles up, or in geostationary orbit 22,000 miles up, and then there's the GPS satellites and a few others that are kind of in between. So let's up the ante, because that was an easy graph. So now we're doing something slightly more complicated. This is the same along the bottom is the height, but now I'm doing inclination. So at the bottom of the plot are all the things that are going eastwards, like I said is the sensible thing to do. In the middle of the plot are the things that are going over the poles, 90-degree inclination. And at the top of the plot are the things that are going the wrong way round, to the west. And you'll notice that the top of the plot's pretty empty, because most countries are pretty sensible, and they launch to the east to take advantage of the free spin of the Earth. And most of the eastward stuff, the geosatellites are all over the equator, which they have to be. And the satellites that look at the Earth, particularly like this SSO area here, which stands for Sun Synchronous Orbit, which is another special magic orbit that's unfortunately a bit more complicated to explain, so I'm going to pass over that for now. And so you'll see that there's a lot of satellites here, a lot of satellites here, and then there's just one or two going the wrong way around. I just made this today. I can't think why I didn't think of doing this before. This is who owns that junk. So blue is America, red is Russia, green is China, and pink here is Europe. And so you'll see that there's sort of stripes of the inclination, because if you launch due east from a rocket launch site at 48 degrees north, then you go into an orbit with a 48-degree inclination. And so these stripes basically are different launch sites. And the Europeans have one in South America near the equator, and the Russians have ones in the far north. And there's actually the Cape Canaveral doesn't really show up very much in this particular plot. You'll also notice the green stuff up here, right, the Chinese debris, right in the area where all the Earth imaging satellites want to be, the sun-synchronous orbit. That's why the Chinese anti-satellite test in 2007 was so bad. It's right in the popular place. Just show you, zoom in on part of that plot. This is the geostationary orbit. All of the operating geostationary satellites in green, that's like 1 mile wide. The magic height at which you have to be at to be geostationary has to be very accurate. And then when they retire them, the red crosses show all the dead satellites that have been moved away from the magic height with their last few gallons of fuel. And this is the area of the plot, zooming in, that shows the sun-synchronous, the polar orbiting Earth imaging satellites, which this lovely equation shows the purple line is where satellites would like to be. And you'll see that all of the green satellites, all of the operating satellites are really near this line. There's none over here, there's none over there. So that this equation, simple equation, really does predict where the satellites are going to be. And then all this black stuff is the anti-satellite debris that's really messing up that part of space. So that's not good. Let's talk a bit about the different kinds of space junk we have. And really, I divide it into two different kinds that I call deliberate littering and accidents. Although not all the accidents are actually accidents. So the deliberate littering is, I've talked about already, dead satellites, rocket stages that you've just left up there, and the jettisoned bits and pieces that you've thrown off. Accidents include, if you have a rocket stage up there, if you go to, there's usually about, some amount of fuel left over at the end of the launch. Maybe a ton of fuel, something like that. And if you go to the grocery store, right, you don't fill your car with just enough petrol to get there and run out when you get back. You always have a little left over. Maybe the engine will run a little hot, so you have to have some spare. So at the end of the satellite launch, you have some spare fuel and some spare oxidizer. Rocket fuel has two pieces to it. And you have maybe a rubber gasket keeping them nice and safe and separate, which 10 years later erodes. And suddenly you don't have a rocket stage, you have several hundred pieces of space debris. We have batteries, have kind of the same problem. There are the accidental collisions that I talked about, deliberate collisions, self-destruct, and breaking up when you get too close to the atmosphere. And so when you sort of census this, when you count up all this stuff, as you see, I have too much spare time on my hands. Since Sputnik, there have been 42,000, almost 43,000 objects added to the satellite catalog. Of those, 18,489 as of yesterday are still in orbit. And those divide up into what are called whole bits. That's the first kind, the littering. That's almost 8,000. And 10,000 broken bits, the accidents. And there's a very fine breakdown there of the different kinds of things that are orbiting the Earth. And the fact that if you divide it by country, Russia and America are, as you might expect, the main culprits. And China is, for the fact that China's had a lot less space activity over the years, is really caught up on the space junk stage. So how do we fix this problem? So I'm going to go through each of these categories one by one and go, well, all right, what's the solution? Because each of them is different. So the dead satellites. Here's a dead satellite. This one got lucky. They launched it. There was an electrical problem. It died. It wouldn't boot up. You know, we've all had that happen to our new toys, right? But this one was lucky because an astronaut came up and rewired it and fixed it. But mostly they don't do that. What you should do in general is while your satellite, well, the first thing is, back in the 1970s, they didn't have any way to fix this because most satellites did not have their own rocket engines. Sputnik, when Sputnik was in orbit, they couldn't change its orbit. It was just going to orbit the way that nature made it with friction with the atmosphere and so on. Nowadays, most big satellites have their own rocket engines to precisely control their orbit, to do various fancy things. And so they can use a little bit of that rocket fuel at the end of their missions to lower their orbits and either get them out of orbit entirely, or at least every bit you lower it means it spends less time in orbit, because the lower it is, the denser the atmosphere, the quicker it'll re-enter. And that'll reduce the probability that the less time you spend being space junk, the less chance there is that you'll hit somebody. High orbit satellites, like in geostationary, so you move them to a higher orbit, you don't have enough fuel to bring them back. Rocket stages. Well, that's also obvious. So again, in the old days, rocket stages, once they'd launched the satellite, usually you could only fire the rocket engine once. And so it had launched the satellite, and then it was done. It couldn't do anything else. For a bit more money, you can design a restartable rocket engine. This isn't as easy as it sounds. You have a rocket, the restart is okay, but getting the fuel to it is not, because you have fuel in the fuel tank that you want to get into the rocket engine. But now the fuel tank is half empty, and you're in orbit, you're falling, you're floating, and so the fuel likes to float into the middle of the tank. It doesn't want to, you don't have gravity to help it go down to the rocket engine. So the way you do that is you have another smaller rocket that accelerates the rocket stage to get the fuel to the bottom of the rocket tank. And so, you know, these kind of, it's a real problem. So you spend a bit more money, and you make the rocket engine restartable, and you bring it down in the ocean, hopefully at the end of the first orbit, as soon as you've gotten rid of your cargo. The other thing you can do, hopefully someday, is bring the rocket stage back and use it again. Many of you know that Elon Musk of SpaceX has been bringing back the lower stages of his space rockets. Those don't go into orbit, though. The upper stages that go into orbit are a harder problem. But in a few years, they'll be doing that too. So here's a typical satellite payload. It has a rocket stage and a pair of satellites. And the top satellite sits on top of this little box, and the lower satellite sits inside it, because if you just put one satellite on top of the other, the lower one will get crushed. And so this thing gets into orbit, and the top satellite pops off, and the adapter pops off, and the lower satellite pops off. So you end up with 2 satellites, but a total of 4 objects in orbit. And so already for smaller things that we used to eject, we now put them on hinges instead of ejecting them. I think, you know, you could redesign this to sort of split open on hinges and stay attached to the rocket stage, and that would be one less piece of space junk, and then make the rocket stage have enough extra fuel to get it back down again. So you could get rid of those 2 extra pieces of space junk with, again, extra money. Lowers the profits, right? But you have to do it by regulation to convince people that it's important not to have the space junk. I think once commercial companies start losing more of their satellites due to collisions, you'll get to a tipping point where they get much more serious about this. This little chap, it's about yay big, is called a SOZ. Systema Obyczajne Zapustki, I think, and something like that. My Russian isn't good. And there were 2 of these little motors on each of the old Russian Proton satellites. And these are these ullage motors that are the things that fire to force the fuel back in the big rocket stage. And then they get jettisoned to space junk. And then they sit in orbit for 10 years. And then they go bang with their remaining rocket fuel. So, in fact, one of those, the satellite catalog just cataloged 12 new pieces of space debris yesterday from one of these things that was launched in 2010 that just blew up. That's an obvious solution is you pay a bit more money, you have a system that gets rid of the leftover fuel, vents it into space during the mission rather than just leave it there. And there's been like 40 of these things that have blown up so far. Made a lot of space debris. So there's a series of weather satellites that were built by RCA in the 70s and 80s. They have batteries that seem to really like to blow up after some years in orbit. So batteries have a lot of energy in them. If you don't vent the battery fluids at the end of the mission, it turns out that they can, well, we've heard about like these lithium batteries on planes that have had some issues, and this is a similar issue. Then the Soviets had a habit of putting self-destruct systems on their satellites. They really, really didn't want their stuff falling into American hands. And so they would, if they thought that a satellite was going to re-enter in the wrong place, they would blow it up. This particular series of early warning satellites had an issue that the self-destruct device liked to go, after the satellite had been retired successfully, liked to go off on its own. After some number of years, again, these things were orbiting Earth and then suddenly bang. And so that's just not a good idea. Don't put self-destruct devices on. And then the thing that's really not a good idea is anti-satellite weapons. At the top right, we have a Soviet system from the 60s, which would approach another satellite in orbit and release a whole bunch of like shotgun pellets that would, with high explosive, that would shred the other satellite to pieces. And then on the left here is a U.S. Air Force F-15 with a big missile underneath it that goes into space and just hits a satellite. There was a U.S. Navy astronomy satellite called P-78-1 that was happily taking data on the solar wind and the sun. And then suddenly their data stream stopped because the Air Force had decided to use it as a target. This is the less pleasant way to discover your mission extension has not been approved. That was 1985. All the debris from that has now re-entered, but it took quite a few years for it all to come down. And then we have the collisions, the satellite collisions, and as I explained earlier, the only way to avoid that Kessler Syndrome is basically to clean up the rest of the junk, not have as many things in orbit. There's one other thing you can do for operational satellites is you can tell them, you can have them maneuver out of the way if you know that the collision is about to happen. That requires you to be able to predict the orbits very accurately so you don't get too many false positives. Otherwise you're dodging all the time and you use up all your fuel. And so we're making improvements on that, but it's, I think, still the major solution to this has got to be just cut down the amount of debris. So I didn't want to end on such a depressing note on how everything's terrible in space. And so I just want to remind you that there's some really promising developments happening. And here's some pictures of the SpaceX Falcon 9 with its reusability, both in terms of the first stage of the rocket and the cargo ship that goes to the space station, which is also being reused on multiple missions. And so that's a step forward. SpaceX has great ambitions. This is the plan Elon Musk just released for a Mars city with a fully reusable rocket called the BFR. So, yeah, that big something rocket. Even the traditional aerospace companies are being much more imaginative now. This is a recent, again, last month study of a Mars orbit base with reusable Mars surface-to-Mars orbit spaceships. And this is built out of, apart from the reusable spaceships, it's built out of technology that exists today for the space station, sort of put together in different ways. And so, you know, there are a lot of exciting things to do in space. And so if we don't, but this is the all this debris from the Iridium Cosmos collision, and just sort of how long it takes to go around the Earth versus how high it is. So we don't want that. We want this. And so hopefully the rules of the road that space agencies are informally developing that go, okay, try and get all your satellites down after 25 years. Don't litter a geostationary orbit. Don't do anti-satellite weapons tests. We'll start to clear up the space debris problem. But as you saw from that graph with the jump where the two bad events happened, it only takes a couple of bad things to make the debris problem much worse. So it's going to continue to be a challenge, and let's just hope that we can clean our act up in space as well as on Earth, and be able to use both in the future for productive things. Thanks a lot.
Terrific. You saw there Jonathan making enormous use of his obsessive database and why it's worth him doing it. Excellent. Please, some questions. Let's see. At the back at the end there.
Two questions. One, can a collision happen so strong that it makes pieces go to escape velocity? And then the second question, what's out at the moon? And your picture of the distance away, you had items out at the moon.
I did, didn't I? Yeah, okay. First question. If you bang each other hard enough, can you get to escape velocity? Yeah, absolutely. In principle, you can. Typically not for most of the actual collisions that happen in practice. You get to apogees, like most of the collisions are going to happen in low orbit over the North and South Pole because that's where all the orbits intersect, right? And those tend to be at velocities where the highest result you get is maybe a few thousand kilometers. It doesn't get to escape velocity. But if you had a bad collision in geostationary orbit, where you're high out of the gravity well and it doesn't take as much energy to escape, you can well imagine that that might happen. The second part of the question was...
What was near the moon?
What was near the moon? Well, there are some probes near the moon. We have a number of... a lot of rocket stages that got our moon probes to where they now are. There are some objects orbiting the moon. And so, yeah, there's a bunch of stuff, and that was a log scale, so on that scale, the moon and halfway to the moon are pretty close. And so Chandra, for example, is a quarter of the way to the moon. So there's a few spacecraft beyond geostationary orbit, not many, but they're mostly scientific ones exploring the outer magnetosphere. Geotail, the Japanese satellite that's been up there since 1992, bumming around in the measuring the magnetic field out there.
Okay. Yes,
yes. How do you know when stuff has come down? I mean, how are you able to track it?
Okay. So the main and of course I don't do it personally, right? The Air Force does most of the work. There's the main way people know, right, is you know that something's in a low orbit. It's going to come down soon. You can model the prediction. And then the next time round, your radars don't see it anymore. And then sometimes you get lucky. 3 days ago, there was a reentry there was the Russians sent a cargo ship to the space station. And of course that put a rocket stage in orbit as well. It stayed up for about 3 days, and then it re-entered. And the folks in Dubai got a really nice light show and thought they were being attacked by aliens or something. And so you do get reports of space debris. Not a lot of space debris reaches the ground, but quite often you get reports of things that look like meteor showers, but a bit different. And they're slower than meteors, so you can kind of tell the difference. So you go, okay, that's space debris re-entering, and then you can kind of match it to what isn't up there anymore.
We had a question at the front here.
Okay, so with the sprites, which are now the smallest satellites, how bad are those going to be for space junk? Because they're so small and there's so many of them.
Right, I didn't mention the sprites. Good, yeah. So I talked about the CubeSats, which are 4 pounds. The sprites are like a few grams.
Credit card size.
Credit card size, yeah, and they're awesome. They're a great invention. But if you launch a lot of them, you might worry that they're very hard to track, so you won't know where they are. So I wouldn't be very happy deploying 1,000 sprites in sort of medium-high Earth orbit. But the plan so far, what Zach has done and so on is to deploy them at below space station altitude, where they'll only stay up for a few weeks. I think anything that's below the space station doesn't stay up very long, and so that's not a big littering problem.
More questions? Yes, sir.
Like, what does one of those little satellites do all up for a week?
The ones that we're talking about are actually they were done on a Kickstarter thing to have your own like bleeping signal with your and they weren't really doing a lot of science yet. But then when the first CubeSats were launched, they didn't do very much, and now they're doing Earth imaging and communications and things like that. You could imagine a scenario in which even short-lived satellites, if you keep replacing them, right, could provide a useful service. So there are a few things that can be done.
Do you have any questions up in the balcony? Yes.
You mentioned some of the space debris. I think it was an active satellite that was going the west.
Yes. Oh, right. Let me see if I can find that. I meant to test you on that one. Let's see. Bear with me a second here.
Wow.
Yes, you're talking about these little light blue ones here.
There was even on the previous slide, there was some right at the top at 180.
I think that might have been a mistake. Let's
There.
see. Oh, there is one. Yes, okay, that's the 10,000 kilometers. That's the science satellite cluster, I think. Oh, no, 180? Not sure. I'll have to check that one.
Cannot be an error in the database. Yes, it can. Of course.
Yeah, well, it could be, but I don't think so. I think it's one of the magnetosphere satellites, but I'm not sure which. But the ones that I mostly see are, and the fact that it's not in this one worries me, because it suggests that it may be the older data set. So here you have these light blue ones that are going west. So the one country that regularly launches to the west instead of the east is Israel. Because if Israel launches to the east, it starts a war. And so they take the penalty of having to use a bigger rocket for the same satellite, just for good reasons.
More questions? Yes, back to.
Are there any international organizations attempting to address this?
So, right, are there international organizations attempting to address the space junk problem? So, the United Nations Committee for the Peaceful Uses of Outer Space, COPUOS, has meetings about this regularly. And in particular, one of the most effective groups is called the Interagency Debris Committee, or IADC, which is basically a committee that meets now and again of the space junk experts from NASA, European Space Agency, Roscosmos, and so on. And so, they do all go together and go, hey guys, what are we going to how are we going to address this? And they've come up with guidelines that are followed more or less, even though it's not an actual law. So there have been improvements. And, the Chinese were slow to pick up on these, but they seem to be doing more of it now. I think that there is movement. But as usual in these things, right, it's sort of, too slow and too little, but it is at least having some effect.
We had a question right up in the balcony there. Yes?
Hi. Didn't Japan recently try to scoop up space junk?
The Japanese experiment that I think you're referring to, called KITE, was on one of its cargo ships. After the mission, they were going to use a tether. So what happens is, if you deploy a wire with a weight on the end that's about like a mile long or something, then the center of gravity of your spacecraft has sort of changed location where its orbit is. If you then let the thing on the end go, it's going to zip up to a higher orbit, and your other thing is going to you're suddenly at the wrong orbit, the wrong height for your speed, and so you fall out of orbit. You end up in an orbit with a negative low point. So that was the experiment that they were doing. And so it's a cheap way to deorbit yourself without using rocket fuel.
Okay.
So that's one of many, and I will say, in the past year, there have been maybe half a dozen, no, actually maybe like more than that, there's dozens of experiments launched with different approaches to how to get small satellites out of orbit. One of the things, the CubeSat will deploy a little parachute that will slow it down in orbit and make it re-enter more quickly, that kind of thing. So there's a lot of work going ahead on this. It just hasn't reached operational status yet.
I had a question. When you launch the astronauts going up to the space station, this debris, they must go through this? Or?
Right. And so the trick is, if you're counting down for launch and you're sitting in your seat, waiting to get boosted up into space, the folks in mission control are doing calculations to go, when's the next piece of space debris going over? Is it going to intersect? And sometimes they go, okay, folks, we're having a 5-minute hold to wait until this piece of space debris goes over. So they actually do sort of air traffic control to do that. Now and again in the space station, they have a warning like, oh, we're going to have to boost the space station's orbit to avoid a piece of debris. Or if they get the warning too late, everybody run into the Soyuz and close the hatches just in case we get hold. So it's an operational concern. Sometimes you say, oh, we can't go today because there was a space debris collision warning, so have to reschedule for tomorrow or something like that. So it's at the level of an annoyance now, but you can imagine again if it were 100 times more, you wouldn't be able to go at all.
We have time for just a couple more questions. The gentleman back there, do you have a question? You did have, yes.
I take it that a CubeSat intersecting the space station in the wrong way would be very disastrous. Is there some procedure so when they release these CubeSats, they keep them out of the way of the space station for their whole orbit?
Right, exactly. So one of the ways that they launch these CubeSats is that a rocket launch is kind of a rough ride. So if you wrap your CubeSat in bubble wrap and give it to a company that's delivering cargo to the space station, bring it up in carrier bags, then they go into the Japanese space station module, load it into a little spring-loaded launcher, and take it out the airlock with the robot arm, and go ba-doing, and put out these. And they've launched a few hundred CubeSats this way. And what they do is they make sure that the arm is pointing backwards relative to the direction of motion, so that the CubeSat ends up in an orbit with a slightly lower velocity than the space station, which means it goes and it ends up going down and it never catches up. Then atmospheric drag is enough to make sure it never intersects with the space station. So they do worry about this.
And we had one more question before. No? Okay.
How was the altitude for Chandra chosen, and are the other space telescopes at the same altitude?
No, so really, to be honest, as far as I can tell, these things go in fashions. Until the 1990s, the fashion for space telescopes was that you went in low Earth orbit, like the Hubble, particularly in the days when we thought it would be cheap to repair them with the space shuttle. Then by the time Chandra came along, we knew that wasn't quite the case. We wanted to be far from the Earth so that you could have, in a long orbit, you can have long uninterrupted observations. And also if you're very high, the radiation belts, you're not going through the radiation belts as much. And so you can have long uninterrupted observations with no background. And that was with no interference from radiation. That was popular for a few years. The European XMM Newton, our sibling, is in a very similar orbit. And then someone realized, actually, it takes very little more energy to get to a solar orbit. And then you don't go in the radiation belts at all, and there's some other advantages. So they put Spitzer, the infrared telescope, in solar orbit. But that has a disadvantage, which is that you end up very far from the Earth and it's hard to communicate with spacecraft. Spitzer was only meant to last a few years, so they didn't think it would be a problem, but they're still going, so it is. So then they went, no, the real place for astronomy telescopes to be is Sun-Earth L2, the second Lagrange point, 1,000,000 miles towards midnight. And so if you take the Sun and the Earth in a straight line and keep on going, 1,000,000 extra miles, so 94 million miles from the Sun, as you orbit the Sun, you want to orbit slower than the Earth, but the Earth is tugging on you, so it actually pulls you along, and you keep in the Sun, you keep in the same line, and that's a stable point, or semi-stable point, and so now that's where almost all the astronomy missions are going, and it means you have the Sun and the Earth behind you, so in front of you is always really dark and cool, and so you put your solar panels and sunshade on one side and look out the other way, and that seems to be currently still the best idea for where to put your astronomy satellites. That's where James Webb is going, that's where Gaia is, that's where Herschel and Planck were, and so a new fashion may come along at some point, but right now, that's where I would buy your real estate.
Okay, I'm afraid that's all we've got time for. Let's thank Jonathan again.